now, so I'm recording, so you can start.
All right, cool. So like I kind of just said, let's like just it simplifies things a lot to think about representations of abelian groups, and then also this is going to turn into um uh the Fourier transform that we all know and love. So hopefully like this can so keep that in mind in terms of where this is heading. But I'm just gonna look at the second simplest abelian group, which is the cyclic group of order 3. And so you can think of this as like 0, 1, and 2 with modular addition, or just like 1x squared. X times x is x squared, x times x squared is 1, you know, et cetera, et cetera. This is abelian, so it commutes. And so when we think about representations and representation theory, what we want is like a group homomorphism to a vector space. And then what that means for abelian groups is that always is just C. It is just the complex numbers, and not even just the whole complex numbers, it is the unit circle on C. And so what this homomorphism ends up being is rotations of, you can think of it very precisely as rotations of the unit circle. But a quick detour. So I talked last time about conjugacy classes, and conjugacy classes are really important because there is one irreducible representation of a group per conjugacy class. And so the conjugacy classes are just, can you get from one, this is like for non-abelian groups, this is kind of this is sort of like as close to you as, this is kind of like how abelian are different members of this group. And it splits up the group into these, it's an equivalence relation, and so you can split up the entire group into these conjugacy classes. But for abelian groups, it's already abelian. It's already everything commutes. And so there's never this like xgx inverse that takes you to a different group element that always just keeps you exactly where you are. And so every abelian group has each element is its own conjugacy class, all on its own lonesome, and that also means that there is one irreducible representation per element of the group. So before, like S5, the symmetric group on 5 elements, has 120 elements and 7 conjugacy classes. So that is very, very different. And one of the reasons that the representation theory of abelian groups is so nice is because you can identify uniquely, each irrep with one element of the group. And so what that specifically looks like is, like I said before, for this, the cyclic group of order 3, and for the cyclic groups of any like finite order, you're mapping the elements to the roots of unity. And so, I spent most of this past week trying to learn Manim because I'm like, clearly, like, what I need for this presentation is lots and lots of like visualizations and animations and stuff. And unfortunately, I couldn't learn Manim fast enough to like put something decent together. But so just like imagine in your head, these are like three, so 3 spokes on the unit circle, and between them is 2 pi over 3 radians of, like the angle is 1/3. And so those two, -1/2 plus or minus root 3 over 2i are the like if you cube those, then they both go to one. In kind of different, in different directions around the circle. Does that all make sense? But so, like, what this means is that we're taking the action of our group, of like the group multiplication, and turning it into complex multiplication. Any questions? Is that like, do you kind of can you see that in your head? I wish I could visualize it for you, but like that is fundamentally what we're doing.
It's too bad about the banning thing, but yeah, I can at least I can
Yeah.
visualize it.
Yeah, Manim is hard.
Manim is hard. I was able to like kind of get it to work, and then, but I didn't understand the API well enough to make it properly modular.
Yeah,
And because I couldn't like really figure it out enough to make it modular, like I was just kind of facing down this like massive, like making just this massive scene of spaghetti code.
yeah, but I
Um,
think that's what it is doing for the channel as well. If you look at I think he published like some of his video, whatever
um,
files, right? And they're just this huge like spaghetti monsters, whatever.
I guess maybe yeah, maybe I will look more at like how what's his face Grant Sanderson does it, and yeah, maybe that is actually just the way. I didn't really want to do that. It seemed rough, but anyway.
I mean, there is like a Haskell library for Manim style animations, but
Oh really?
yes.
Oh interesting. Yeah. But yeah. So just just imagine in your heads or draw like that these kind of just rotate, that you're just rotating the circle, and that you can kind of cyclically permute these elements of the group by rotating them around a unit circle. um and then yeah, and then just kind of to really make this explicit, this is true for all cyclic groups, then the irreducible representations are just mapping, and thinking of it specifically as like 0, 1, 2, like the additive group mod, n, then you're just taking your group element and then doing the complex exponential of that divided by n, and you get these complex roots of unity. And I suppose actually the other thing that I should think of that is a little bit subtle is, so so um there's three irreducible representations, and and even though, and this is important because this distinction become like something is kind of easy to elide here, is that so the irreducible representation is still a map. It's still a function that acts on each element of the group. And so the trivial irrep is a map that maps every single element of the group to one. And then one always gets mapped to itself, or like the identity always gets mapped to one rather. And then there's two more, and uh, and so there's two more cube roots of unity, and in one irrep, they're assigned one way, and then in the next irrep they're flipped. Um, and so because there's like three irreps, and you can be like, all right, there's the irrep that maps to the identity, and then there's another irrep that maps to the first root of unity, and then the third maps to the, or yeah, maps to the other one. Um, it's not mapping like a number to a number. It's mapping a group element to a map, or it's like, yeah, it's mapping a group element to a number, or a set of numbers. Um, does that and this will be important because that's what's happening in the non-abelian cases, like the same way. Even though there's now like, there's only one irrep, the irrep is mapping a group element to um, in this case, in that case, like a matrix. But I don't know. Is this making sense? That it's not just like, oh, there's one irrep, and it maps like x1 to -1/2 plus square root 3 over 2i. It's like there's one, like in one irrep, x1, or in the first irrep, x gets mapped to that, and then in the next irrep, x gets mapped to its conjugate transpose. Does that distinction kind of make sense? Maybe not explaining that well. But so this works for all n, and this is actually true, that all abelian groups are maps, like all complex irreducible representations of abelian groups are maps from the group to the circle group. And if it's and like you can also kind of do it, if it's like a product abelian group and it's like C3 cross CX or C6 or something, then you can, it like kind of will become like on a torus if you want, but also you can actually still just map it to these roots of unity. And so like fundamentally what this is about, and this is also actually why I was asking about the Yoneda lemma, but these, the circle group, or there is some circle group that is the dual group of every abelian group, whether it's finite or infinite. And, and so you can, any function on the group, you can flip it, you can transform it to a function on the circle group, and you get basically the same function, but you can kind of look at it in a whole new light. And so just, to make this, I guess like, I like making these things concrete because it helps, bringing it to earth helps me understand, like this is what I do when I like am trying to understand these things. But so, if we have a function on a cyclic group of order 3, it's really, it's really simple. It's just these kind of 3 maps. And so if we have this, f of 1 is equal to I, f of x is 1 plus I, f of x squared is 1 minus I, then like what does it actually mean to take the Fourier transform of this function? And so this is the formula for the Fourier transform. And basically the steps are always kind of the same, and whether you're doing this for an abelian group or a non-abelian group, the trivial representation, the Fourier transform of the trivial representation is always just the average. Like that row triv of pi always just goes to 1, and then so you're just taking the mean of the function over the entire group, and you get the average. And then this is kind of important because when you take the reverse, like you realize that the function on all of the other irreps are in relation to a zero mean function. So this is like a lot of this is like a lot of equations, but just going step by step, like so and recall the first like if we just expand out that sum, we're taking row 1 of 0 is still just 1, so it's like just that f on so it's f on I don't know, maybe I don't need to kind of explain this, and it just you can just kind of look at it, but it's like these these are like the steps where you just are you just kind of fill these things in, and I don't know, and then we don't need to do it again. But I guess the one thing that I'll say is that, yeah, like the difference between this and this is that like these, or these two get switched around. And yeah, so because this is an abelian group and we get one irreducible representation per element, we just get kind of this other version of the same function, and no information is lost. And we know that no information is lost because we can go from one to the other, and because this is, oh, I messed up the LaTeX, and so specifically, I guess what I feel like, when you see something like this, which is like, oh, like, did steal this from 3 Blue 1 Brown, when you're like, okay, like the Fourier transform means that I can add these functions together, or like I can decompose my function as a bunch of sine curves. What that really means is that, so you can get, so f hat is our Fourier transform. You can get f back at any point as this kind of weighted, this equation is a weighted sum of sine curves, because and it's e4 pi I of x. Okay, anyway, I also messed up the, but so the e's, the exponentials on the outside should have like an x in them as well. But this is like a weighted sum of sine curves, and this I guess I don't know. Maybe I really should have figured out how to visualize this. But this equation of going back and forth is the same as what we were doing in the finite case. And actually, it's, when you do a discrete Fourier transform, it's precisely the same. And the whole point is that this row of one, or these rows are functions. They're maps from the group to, each row is a distinct map from the group to, the circle. And in the continuous case, you get the sine curves. And so this is it. This is the decomposition of how you, this is actually what it means. Does that kind of make it sense? Or am I still, are there any questions at all?
I mean, the intuition I always rely on for the Fourier transform is that you're basically using an orthonormal basis of your space of signals on whatever you're studying. So here we have signals, so functions defined on a group. Mm-hmm. We're just using taking an orthonormal basis of that function space.
And that was the whole kind of point of everything that we were doing in the last 2 weeks in terms of finding ways to, when we talk about, so thank you for pointing that out. When we're looking for an irreducible representation, and we were like, well, so what are the irreps? What does that even mean? We went to all of that work of figuring out what these irreps are, and then we happened to discover that, what this means is that any function on this group can be broken down in this really precise way that is, it's orthonormal, it's, it provides a basis for all of the functions on the group. And because it's orthonormal, it's really sparse. Oftentimes, I mean, I guess not necessarily, but usually the kind of interesting thing is that if something is sparse or what tends to happen is if something is sparse in the Fourier basis, then it won't be in the kind of like standard basis. And if it's sparse in the standard basis, it won't be in the Fourier basis. But so of the two, one will be pretty interpretable. But you have these kind of two natural choices of bases for your function. And yeah, and it's all like you're looking for these simple contained subspaces that the group acts on. And for every abelian group, it is these rotations of a circle, rotating it either very quickly or very slowly. Yeah, I don't know. This blew my mind when I kind of realized it. I'm like, oh, this is where those sine this is where those sine curves come from. It really didn't, yeah. Any other questions or comments? Um,
I think Nev might be trying to say something, but I can't hear him.
oh, Nev? Yeah, I can't hear you either.
Wait, who?
Nev, the orange fractal guy.
Ah,
Yeah. Well,
Okay, Mike Tyson
maybe it
disconnected.
was. Um. So yeah. So taking this. So I guess I'll move on, but we can go back at any point if anyone has a question. Um. So on a non-abelian group, this is the same thing almost, except so like this is basically the same formula, though now the rows are maps to matrices. And the different rows may not even be the same dimension. And so like the f of pi is still a scalar, and so that's scalar multiplication, and I have that dot there because sometimes I don't know, in other cases it'll be f hat and like no dot is going to mean matrix multiplication, but so it's a scalar sum of it's like kind of this weighted average of all of the representation or all of the matrices in a representation. But you don't get this like you can just kind of add things together anymore because the units just don't really work out. Yeah, so you can't you could literally just go through in the abelian case and just sum up the different contributions from different irreducible representations, but it doesn't really work like that in the non-abelian case. And so this is why, this is what the formula, the inversion formula properly looks like for the non-abelian case, and basically you need to weight by, so the d row is the dimension of the matrices, of the dimension of the irreducible representation, and then you're taking the trace, and that is kind of how that works. And you send everything to scalars, and you can add things together again. And so so this gets complicated because it gets complicated to interpret and it gets complicated to calculate, but you can still do this the same thing where oftentimes the irreducible representations are these kind of almost frequencies that will encode interesting things, like it'll make things about the group or make things about the function more clear. And so I just kind of wanted to run quickly through. This is the example that was in Diaconus. And so, you know, here we can think of, if you did a survey and you had people rank what they liked best. And in this case, it was, do you like to live in the city, or do you like to live in the suburbs, or do you like to live in the country? And everyone had to rank them, 1, 2, 3. Then each possible way to rank those three things, we can think of as an individual, as a permutation. And so we can think of this function as from a permutation to the count, the number of people who like picked that specific ranking. And for something like this, one reason, I don't know how many of you have ever been, my first job out of college was as a data scientist, and I had to analyze data like this sometimes. I kind of wish I had known about this technique, because it was really not clear where to even start. But one right away, one really nice thing about trying to look at the Fourier transform is that you I don't know, it just gives you a principled way to kind of go about this analysis. And so, similar to what we did before, I'm actually just going to kind of try and go through the calculations. And so the first thing is that you always just take the average, and that is the first component of the trivial representation. And then, because this is the symmetric group, there's an alternating representation, which gives, so trivial representation maps 1 to everything, and that's how you get this just nice mean thing. And then the alternating representation is whether or not there is a difference between the even and odd permutations. And so at this point, you might be thinking, well, wait, isn't this this is a weird thing to look at for because for this ranking data, because then doesn't this depend on doesn't this, if this depends on the cycle length, doesn't this depend on what the we chose to represent this as city, suburbs, county, 1, 2, 3, but then which permutation is which really depends on it would change if it was suburb, city, country, or country, suburb, city, or whatever it would be. And that is true that this function would change, but the Fourier transform actually wouldn't, because every different way that you could order these, or each one that you would kind of pick to be the identity, is just a translation of the entire function by a different permutation. And the Fourier transform is totally invariant to translations. And so you might still think okay, but then why all right, fine, that saves this, but then why would I want to calculate this? And indeed, it would be really weird if for this type of data, this was a really big part of the function, and we will get to that. But so we calculate this, and it is, and so we split up the function by, whether or not it's an even permutation or an odd permutation, and we just subtract the odd from the even values, and we get 325 over 6. And you'll notice, or you'll recall, but so like the trivial representation is 1,439 over 6, and so clearly, like I guess this actually just kind of makes sense that nothing's really going on with even versus odd permutations. But you can imagine data where this actually does, this would make a lot more sense. And so if you looked at some of the other stuff in the Diaconus book, there are lots of types of random walks that you might do on permutations where it's like constant on conjugacy classes, and and so you will really expect this to be a meaningful difference. But so not much going on with like even versus odd permutations. But then quickly, so there's one final like matrix irreducible representation of the symmetric group of S3. And basically, oh boy, I messed up my LaTeX again. But basically what you do is you take the kind of standard presentation, which is 3 by 3, and you just kind of permute the basis vectors. And so like that matrix, that anti-diagonal matrix is, I've switched the first and third basis vector. But if you look at that and you have your standard presentation, then you'll notice that there isn't an invariant subspace. And that is if all of the, like the basis that is spanned by all of the line where all of the coordinates are equal does not get affected by this representation. So what you do is how did I do that? Oh, okay. So what you do is you project onto the orthogonal complement to that, and that is the space where x plus y plus z, like the three basis vectors, are equal to 0. And so this is just, little linear algebra refresher. This is what it means to, so you get these two basis vectors. Oh, and I guess you can't see those two basis vectors. Well, okay. So the two basis vectors are 1, -1, 0, and then 0, 1, -1. And then this is linear algebra refresher, what it means to project, to project these 3 by 3 matrices onto the 2 by 2 matrices, or, onto this 2 by 2 subspace. Does this all kind of make sense, like what we're doing to construct the irreducible representation? But anyway, so we use the irrep, and then we also actually, you want to make this orthonormal, and so, you just, you get a lot of square root 2s and square root 3s to like make everything orthonormal, and then you get, and then I'll spare you the calculation of like this weighted average of all of these matrices, and this is what you get. And you might be like, all right, well, the fuck does this mean? Like, great, I have this matrix, but it's actually really, but it's actually kind of nice and clear, because the biggest component of this is the biggest component of this is the -947 square root 3 over 2, and you can kind of go directly and inspect how that, so you can go and you can inspect like how this individual piece of the matrix affects the function. And the way you do this is you're like, all right, how does this like work? And so the way in the inversion formula, this A, B, C, D is going to be the irreducible representation for pi inverse and then you take the trace of this. But like what is really going to happen here is that you're going to get a times, so the first row AB times the first column, or dot the first column. And so you're going to get negative 947 square root 3 over 2 times B. And you're like, okay, so B, what, like, and this does, this is a little involved. And so this is why it is more complicated than just kind of taking your abelian, but basically like of taking your Fourier transform of an abelian group, but but this is actually what you do because in the for the functions on your group, it is actually these matrix entries of the irreducible representations that provide the orthogonal basis for the functions on the group. And so you really do want to look at these individual entries and kind of how they affect the function. But so, all right, we look at the top right corner of, this B, the top right corner of the arreps, and basically, like, so this is pi, and then the top right of pi inverse is like what we're looking at, and basically, like, there's nothing going on if country is rated last, like that is kind of the mean thing. This is kind of the average, but then the big effect is, like apparently, like most of what the information is in our whole survey is kind of in this difference between whether you rate the city or the suburbs last. And I don't know, like that we can like kind of look back at this, and I guess and I don't think that was really obvious to me, or maybe it was because the two biggest things are, you know, having, well, wait. Well, yeah, no, this wasn't really obvious to me because like the biggest thing is like, oh, the most people have the suburbs first, but they do have the city last, and I guess the second biggest is having the city, or yeah, I guess the two biggest have the city last, so maybe that makes sense. But I feel like just the way my brain works, I probably would have focused more on what was getting ranked first, or different stuff like this. But I don't know. Like it's just an interesting. It's another way that you can do this, and it's pretty useful. And yeah, I guess I don't know, and ending kind of lamely, but yeah, I guess this is all like, does it kind of all make sense, or not all make sense, but do you kind of get a sense of like how you do this and how, like, I think the takeaway, like the number one takeaway should be that you have these two spaces, these two different orthonormal bases for your functions on the group, and I don't know, it's math and it's really cool. uh,
Yeah, I'm a little bit confused about the last explanation, but
I mean, what do you?
so can you go back to the slide where, so I think before that, so yeah, the slide where you show the inverse formula for the two-dimensional representation. So okay, yeah, the idea is that you make this product of the inverse of
Mm-hmm.
the inverse element, representation of the inverse element
Mm-hmm.
times this Fourier transform.
Mm-hmm.
And so because the dominant element in the matrix is this minus 947, it's
Mm-hmm.
this B that's going to dominate, or that is going to be the most important, right?
Yeah. So like, so in so when um so when so something that I should have called out, and also like when you look at the formula for your regular Fourier transform, you'll actually notice that it's always a negative 2 pi, and that is actually this thing of like where you look at the inverse of your frequency, like the in you know or like you look at the you're looking at the negative of your group element. um, and it goes back to like the reason for this is convolution. But so in the abelian case, you just add these up, and there's only one term per, it's just one scalar um, per irreducible representation. Um, in the non-abelian case, um, do 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 do. Yeah, so what it is, it like you can do this same thing where you break it up as a contribution from f hat of the first irrep, and then f hat of the second irrep, and then f hat of the third irrep. Um, but you and so so you can like expand this sum, but then you still have this trace of this matrix multiplication. And so if first you expand the sum, um, then you would, if you really want to just get scalars, then you expand the trace, and to do that, then you're looking at this matrix product. And so what I was showing you was just what was in the brackets of the trace on this final line. Does that make? And then so we can kind of go back.
Yeah, that part is fine. It's mostly the
Mm-hmm.
interpretation that, okay, because this element is by far the biggest, it's going to be the B element that sort of contains the most information.
Yeah. Well, so I guess let's where is the can you still, am I switched to Diaconus here?
Yeah, yeah.
Um, so he maybe does, like, you can actually kind of see this better in,
Yeah, but you might want to zoom in a little bit.
sorry?
You
Yeah,
might
yeah,
want
yeah,
to zoom in
yes.
the PDF.
Yeah, one second. Um, okay, can you see this?
Yeah.
So this is what he has, and it's like basically like this for f of pi, it's this whole sum. Um, and I suppose like the way to interpret this is um, that if cities, and then this is kind of the what he takes as well, like if the country is ranked third, then this B is 0, and the dominant contribution of everything is just the mean. Everything else is like plus 325 this, minus 285 that. You know, like the for the for the elements, for the results of this survey, ranking the country third is just kind of the mean response, and you don't get any contribution from this really big thing that changes it. Um, and but if cities are ranked third, then you get, and it's like negative times negative is a positive, and so like you get this really big kind of contribution of you know um, because cities are, the two biggest responses have the cities ranked third, this 628 and this 359. um, and um, and so like um, yeah, and versus if the suburbs are ranked third, then it's this, this really big contribution reducing it. Um, and so like this, like the variation from different permutation to permutation, the big piece of it is this variation of whether you're ranking the cities or the suburbs third. Does that kind of make sense?
Yeah, that's a lot clearer.
Mm-hmm.
That okay, it's like this particular class of permutation, I guess. So whether or not you're ranking
Mm-hmm.
suburbs or cities first, that
Yeah.
that matters the most.
Yeah. Well, and so again, like this is like it's a method of data analysis. It's a way of decomposing kind of these functions, but the whole, like it will, you know, um, for a yeah, for a different, for a different set of data, um, it will kind of come out differently, and whatever will be kind of the biggest part of it. Like this isn't even running a regression. This is literally like just a, like this is just the data of the function. Like we're just kind of looking at um, uh, it's just looking at the function in through a new lens. It's not even like we're kind of using it, it almost sounds like we're using the language of like regression of like, okay, well, what's the biggest contributor of this, or like what has the biggest effect? But it's actually the same data, and it's just kind of more clear this way. I don't know. Does that
Yeah, I
or
guess
well, or maybe it's not more clear. I don't know.
I mean it's clearer. I think like maybe the biggest difficulty in this part is that you sort of get have to spend enough time to get used to interpreting these permutation
Yeah.
or Fourier modes.
Mm-hmm. Yeah, it is. It is. It is strange enough, and it is like, and I think, to be honest, I think this is probably part of the reason why it's not more widely known. You know, if this were just as if this were as easy to use and interpret as the traditional Fourier transform, then this is the kind of thing that would be taught to all of us in undergrad, as opposed to being this thing that like was in vogue in the 80s, and also like I don't know, like it's now it's kind of a niche, um it's kind of a niche mathematical thing, and so you really do need to kind of dig into like, all right, well, what does this mean, and like what to yeah, like what do each of these um what do each of these matrix entries of each of these irreps actually mean? And it's unnatural for sure. Um, but I I don't know. I guess.
I mean, it still feels really cool as like the
Mhm.
sort of mathematically natural way to analyze data or ranking data or permutation data.
Yeah, I think and I guess that is kind of where I you know like because I mean it's also like like I think about this when like I think about language models, and at each point of a language model, you can think of the logits as a ranking of um, you can think of the logits as a ranking of like the next tokens, and if you just pick like an order for the tokens, then that is a permutation of the like that is a potential permutation of like the tokens. Or you can think of like a function that like a language model that puts probabilities on the likelihood, yeah, like gives you like the likelihood of a sentence, um, and and then you can imagine like probably for a relatively short sentence, say of like 10 or 12 words, there's a few million different orders of words that uh, um, there's a few million different orders of word of ways you can order those words, and um, and the likelihood of each of the that your like language model gives for the likelihood of each permutation of words is is also like ranking data that you could kind of think about using these techniques to analyze. And it's really hard to like we have a lot of people in Eleuther who work really hard to think about how to um, try to kind of interpret um, this sort of data, and and it because it's not like normally distributed like scale just kind of like multivariate Gaussian kind of data, like the tools are more limited, and it's just really difficult. And like this is difficult as well, but I think it's valuable to like just have to be able to like have this perspective. And Yeah, I don't know, but yeah.
I'm guessing a major difficulty is also just computing these irreps and doing this
Mhm.
Fourier analysis with these irreps. That yeah, as soon as you scale the
So so the thing is, I mean, you can actually like I still have not done the fast Fourier transform, but Rizy Condor in 2008 was able to do the Fourier transform on like S12 in like a minute on a 2008 PC. Um, you can get a pretty fat, you can do this pretty quickly. There is it's not like, whatever n log n, the discrete Fourier transform is, um, but it's pretty fast, or, relatively fast. It would still be like S100 would be really rough. But, uh, um, uh, but yeah, like you basically can use cosets to really speed it up, and do this kind of hierarchical decomposition of calculating the irreps. And and yeah, I honestly think that like if someone really put in the effort to like do it on to do like a GPU accelerated Fourier transform on the symmetric group, like it could get quite fast. Um,
yeah, that would be really cool.
yeah,
So
it would.
you should write a Julia package for it.
Say that again.
You should write a Julia package for it.
Yeah.
I want to say I was thinking about it.
Yeah, I mean, I have, I mean, Reese Condor, he's got a whole, like, he tells you exactly how to do it. I mean, it would be tough to, I have a slow version that is, I mean, uh, um, but the real tough thing would be optimizing it properly for GPU acceleration, and like I think like the way you would want to do it is honestly like or yeah, I don't know. You would have to think carefully about how how big the matrices are, and like does it make more sense to just like kind of like pack them into like these big diagonal matrices, or I mean, yeah, I don't know. Like I'm not entirely sure. I don't really know very much about squeezing the most performance out of a GPU in that way, but I think it is just matrix multiplications, and so theoretically it should be doable. I don't know. I don't know.
I mean, would you even need to instantiate those as matrices actually?
That is actually another good point. Is that you would maybe just want, well, yeah, I don't know. That is a good point. I'm not sure. The individual irreps are quite sparse. They have each irrep, each individual irrep for like one permutation has elements on the diagonal, and then max one other element per row.
Yeah,
You know.
that's pretty fucking sparse. So
Yeah.
yeah.
So but then if you have like 10 million of them and you're adding them all up, like at what point does it get not sparse? I don't really know. So um but yes, it's quite sparse, and I think that's also a big part of why he was able, like, again in 2008, Risi Condor was able to get it so quick. Is it was like he just did it all as like on CPU. He just did it um, all sparse all the time. Yeah, I mean maybe honestly it actually wouldn't be that much faster on GPU because most GPUs not have great sparsity support. Maybe it wouldn't really help. I don't know.
I mean, you can always have. I mean, it wouldn't be like a proper sparse math mode, but you can probably do some things. Like GPUs can do other things than just matrix multiplications.
Yeah, I mean the other thing that I have kind of thought about is, so one of the cool things that about Fourier transforms is that um, in Fourier space, convolution is just multiplication, and that is also true for this. It just becomes matrix multiplication. Um, but so you could imagine having like a sequence model, and especially like if you did kind of in blocks of six or something like that, you could imagine doing a Fourier transform over blocks of six elements of your sequence, and then like basically doing learning uh, learning convolutional kernels over like different ways that you would permute elements of the sequence. I actually don't know if that would be helpful in terms of modeling, but I think that you could do it very efficiently for like small blocks, and and it would be mathematically quite cool, yeah, just very quick to calculate in Fourier space.
Yeah,
But
this is actually what people do for like 3D geometric model. They calculate circular harmonics and then multiply it all in circular harmonic space.
yeah, um, yeah, no, I don't know. There's just a really a wealth of possibilities, and in terms of thinking about your data in what is often a more natural way, like this, and kind of taking the structure of your data seriously like this, and yeah, and at least for like convolutional neural networks, like it has been wildly successful, and I think it's been tougher for other types of neural networks, and other kind of types of equivariant models. But I still think that there's a lot of possibility here, and yeah, I don't know. I think I just find it all very exciting.
Uh, do you know of any other groups other than the single group for which there's a fast algorithm like the F15?
Can you say that again?
Do you know of any groups for which there's a fast algorithm for computing the Fourier transform, like for single group there's the F15?
I I don't know. I don't think. I'm not sure. Yeah.
Okay, then. So I guess we're done for today.
Yeah. Um.
Yeah. So thank you
Can you
again
put?
for this. It was pretty
Mhm.
nice.
Yeah. And can you post that in chat, Nev? And I'll try and think about it more and get you a better answer. Um. I don't know. Um. but yeah, thank you all. It's been a lot of fun really digging into this, and I feel like I understand it a lot better for myself.
Cool. So I guess we can move on to discussing what we do next. So if I remember correctly, the topmost item on the poll was topology. So I guess we can move on to that.
Sounds good to me.
Okay, then I found so I had a couple of sources for that, and I found one that was interesting. Actually, I found two. One that seemed pretty formal, and one that's almost immediately had like a very interesting example of like I think using topology for a number to prove that there are infinitely many primes. So I think I'll go with that one too. So
Oh,
yeah,
was this the last meeting for Rep Theory?
I guess more or less, unless we decide that we have more to say about it.
Yeah, I mean, if people really want, I think I'm done for it for now. Like if people really want, then I suppose like the kind of the final thing that would properly cap this off would be to look at like the kind of machine learning group convolution models. Like the steerable CNNs that like Taco Cohen did. Um, but but I think I would like to take a break from this for now. Like I've been thinking about other mathematical things, and I want to keep as clear a headspace for a little bit as I can. So yeah, but I think for now we're no more representation theory.
I could prepare something about like harmonic CNNs.
That would be awesome.
Yeah, it definitely would. Yeah, I mean, let us know
Yeah, when would you be able to do that?
in the thread. Yeah, when will you be willing to do that and other stuff.
Yeah, I'm free this week. I'll look at it and see if what
So,
is ready.
like to give you an idea of the schedule. So I guess with topology you have maybe one, maybe 2 or 3 weeks, and yeah, like if you want to do it in not next week but in 2 weeks or in 3 weeks, like we can slot you in.
That sounds fine.
Cool. Then I guess unless there's other comments or questions. Apparently not. So yeah, thanks everyone for coming. Thanks you Dashiell for guiding us through this nice topic.
Yeah, absolutely. Cool. Well, see you all next week then.
Yep, I'll post the readings then. Bye.
Take care.